Hello. 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 Dear students, am I audible and visible to you? Hello my dear students, am I clearly visible and audible to you? Okay, so shall we start the course? So here I am going to start GTQ series 2025 for power electronics. So we have started this GTQ series in the year 2022 for all the subjects just before the GATE examination. So we here explain most of the important questions in for GATE examination. Okay. So let us go through the first question. Yes, dear students, go through the first question. Yes, a single phase half wave rectifier with freewheeling diode is feeding RL load. Consider the ripple free load current and find the power factor of the source at the source side. Yes, dear students, try to solve these questions. It's a very simple question. A single phase half wave rectifier with freewheeling diode is feeding RL load. Okay. Yes, all of you try this question. So here, what is the output voltage here across the load? Up to pi, this diode is conducting. This is same as the supply voltage, and after pi, freewheeling diode is conducting the constant load current, and it is very clearly given that load current is ripple free, it is constant. Okay. So what we have to find out? Power factor at the input side. So what is the average voltage expression here? Average voltage 1 by time period into area of the waveform is integral 0 to pi. Equation of the supply voltage is given by Vm into sin omega t into d omega t. Okay, so you will get average voltage equals to Vm by pi. So average current is average voltage by load resistance. So here average current will not be affected by load inductance. Okay. So that is equal to Vm by pi into R. So peak voltage is 240 root 2 divided by pi into resistance is 8. So calculate this value. You will get 13.5 amperes. 13.5 amperes. Please verify this one. 13.5 amperes. So I want to find out the output power. So how do you calculate the output power here? Output power is equal to, since RMS current whole square into R, RMS current. Whenever there is power loss in the resistor, consider RMS current, because it is constant current. For constant current, average current, RMS current both are equal. So I can straight away write it as average current whole square into R, because the load current is constant. Average current is 13.5 whole square into 8. So calculate this value. So what is the output power? You will get 1459 watts. 1459 watts. Verify this one. 1459 watts. Is it okay, all of you? Now whenever they are asking power factor in rectifiers, use the power balance equation. So let us assume that it is a lossless converter. Input power on AC side is equal to output power on DC side, assuming that it is a lossless converter. Okay. So input power on AC side is supply RMS voltage into supply RMS current into power factor. Output power already we calculated 1459 watts. So from this equation, power factor is 1459 by supply RMS voltage is 240 volts into, how do you find supply RMS current? How do you find the supply RMS current here? Look at the circuit diagram. Supply RMS current. So this is the supply current, right? So supply current is sharing the constant current for pi radians. So look here, up to pi radians. Let me draw the supply current waveform. You will get the supply current up to pi radians. After that it is 0 amperes. Okay. So from this equation you can write supply RMS current is I naught for pi out of 2 pi whole power 1 by 2. So that is nothing but I naught by square root of 2 supply RMS current. Okay. So what is I naught? 13.5 by square root of 2 supply RMS current. So just calculate this value, 0.637. So that is the answer. Is it okay? So everyone got the same answer, I hope. Yes. See, some of the students have mistaken. They have said 0.707. That is wrong answer. Okay. So answer is 0.63. So unfortunately people will do some mistake here. They will use this formula here. See here, some of the students used this formula. Power factor is output RMS voltage by supply RMS voltage. This is for pure resistive load. This is not valid for RL load. See here, this formula is not valid for RL load. This is for pure resistive load. Some of the students used this formula and got the wrong answer here. So okay, so be careful, my dear students. Whenever you remember the formula, see, this formula is applicable for pure resistive load, but in our case it is RL load. Okay, so be careful, my dear students. Okay, you have to understand your mistakes. Normally question is very simple, but some of the students will unfortunately answer, they will use this formula and they will get a wrong answer here. Okay students, so understand your mistakes. Whenever you remember the formula for what is the load, which case it belongs to, you have to understand. Okay, fine. I hope it is clear, students. Very simple question, right? Yes. Go through the next question here. Yes, dear students, try this question. All of you try this question. Yes. Yes, make it fast. Abhishek, your answer is right. Very good. Am I clearly audible, students? Are you having any disturbance in my voice? Hello, students. My voice is clear? Okay, fine. Yeah, go through this question. All of you solve this. With 20 ohms per phase shown in the figure, VSI operates in 180-degree conduction mode. What is the average supply current? What is the average supply current? Yes. All of you try this question. So here 180-degree conduction mode. Okay. 180-degree conduction mode, line voltage RMS equal to root 2 by 3 into DC supply voltage. So this is the DC supply voltage 500 volts. Okay. So for delta connected load, phase voltage RMS is same as line voltage RMS. This is for delta connected load. Okay. This is for delta connected load. So that is same as root 2 by 3 into 500 volts. That is the phase voltage RMS. Now what is the output power? The power loss in this load. I want to find out the output power, means power loss in the load. So output power, because it is 3 phase, so 3 times of phase current whole square into load resistance. You can write phase current is equal to phase voltage by load resistance. So that can be written as 3 times of phase voltage whole square by R. So okay. So substitute these values. 3 into phase current whole square is 2 by 3 into 500 whole square. Okay. So 2 by 3 into 500 whole square by resistance of the load in each phase is 20 ohms. Okay. So tell me what is this value? Yes. So what is the answer? Output power is 25 kilowatts. Output power is 25 kilowatts. Yes, verify that one. Output power is equal to 25 kilowatts. Okay. Now use the power balance equation. This is DC side and this is AC side. Assuming it is a power balance equation is input power on DC side is equal to output power on DC side. This is DC side, this is AC side. So what is the input power on DC side? DC side supply current is IS. So input power on DC side is Vs into Is is equal to output power is 25 kilowatts or 25 into 3 watts. So supply current is equal to 25 into 10 power 3 divided by supply voltage is 500 volts. Okay. So answer is 50 amperes. Okay. So 50 amperes. So option C is the right answer. 50 amperes. Yeah, right. Yes, very good students. You have done well. Yes, Right answer. Okay students. Yeah, go through the question number 3. Yes, all of you try the question number 3. Yes, go through the question number 3. Which of the following statements are correct for power MOSFET? The MOSFET have vertical oriented structure with lightly doped drain, drift region and highly interdigitated gate cathode structure. Yes. Is it true or wrong? First statement. First statement is true or wrong? Dear students, yes, first statement is right or wrong? First statement is correct or wrong? Yes. Ankit, yes, you are right. Once again go through this. MOSFETs have vertically oriented structure with lightly doped drain, drift region. What is this lightly doped drain? Lightly doped means N minus layer. That is called, what is the use of N minus layer I said? And highly interdigitated gate and source structure. What is this interdigitated gate source? Dear students, what is this interdigitated gate source structure? Just let me redraw this structure of MOSFET here so that you will get some clarity here. So N plus layer you have, here N minus layer you have, P layer, here we have P layers, this is N plus layer, here also N plus layer, here also N plus layer, right? And here we are having SiO2 layer, okay? See, this is SiO2 layer, SiO2 layer, okay? Then next, so here we are connecting, see here, this is the metallic surface to take the drain terminal and this is the source, okay? And somewhere here we have gate terminal, this is the gate terminal plus and minus, okay? So dear students, if you look here, alternately we have gate, source, once again we have gate, source like this. So this is called interdigitated gate source structure. You understood? So for MOSFET we are having interdigitated gate source structure. This is the known as, okay? See, alternately this is the gate, source, again this will stretch like this, gate, source, that is called interdigitated gate source structure, okay? Yeah, first statement is right statement, okay students? First statement is perfect. Yes, right statement. Dear students, I hope you understood. The first statement is perfect. Go through the second statement. Yeah, go through the second statement. Yes, just go through the second statement. On-state losses in a MOSFET rise much more rapidly with blocking voltage rating when compared with the MOSFET. So did you understand the second one? On-state losses in MOSFET will increase much more rapidly with blocking voltage rating when compared with the power MOSFET. You know, in the case of MOSFET, it behaves as resistance in the on state, so that will increase the losses in the device. So conduction losses is more in MOSFET when you compare with BJT, and that will increase very rapidly as the voltage rating of the MOSFET is increasing when you compare with BJT. Yes, so this is also right, correct statement. So B is also correct statement. Okay. Okay, so B is also correct statement. Then what about the next statement C? What about the next statement C? Dear students, go through the statement C. The on-state resistance of MOSFET has negative temperature coefficient because it is a majority carrier device. Yes. Statement C is true or false? Statement true. Statement C. Go through the statement C. Is it true or false? Yes. So this statement is false statement. Okay. See, this is false. MOSFET is having positive temperature coefficient for on-state resistance. So that is false. Next, last statement. Go through the last statement, dear students. Last statement. Go through the last statement. The requirements of snubber circuits is reduced in MOSFET due to the large safe operating areas when compared with power BJTs. Yes. Convey the message. Last statement is true or wrong? True or false? Last statement. So what do you understand by safe operating areas of a transistor? See here. Safe operating area of a transistor. So here safe operating area explains all the possible operating points within which the device is safer to operate. Okay. Now in the case of MOSFET, we don't have secondary breakdown limit. See, what is the disadvantage with BJT? BJT has secondary breakdown due to negative temperature coefficient. BJT has secondary breakdown. BJT has secondary breakdown due to negative temperature coefficient for on-state resistance. So because of secondary breakdown limit, safe operating area is lesser in BJT. So therefore safe operating area is lesser for BJT. That is why we need snubber circuits. You see, if safe operating area is lesser, the possible operating points is not possible. So that is why we need snubber circuits for BJTs because of secondary breakdown. But MOSFET is having positive temperature coefficient. See here, MOSFET is having positive temperature coefficient for on-state resistance. So therefore secondary breakdown will not occur. Therefore secondary breakdown will not occur. Secondary breakdown will not occur. So therefore safe operating area is more in MOSFET. That means the operating area is more for MOSFET when you compare with BJT. Therefore safe operating area is maximum for MOSFET. Is maximum for MOSFET. Okay. Safe operating area is maximum for MOSFET. Okay. So that is why the requirement of snubber circuit is reduced in MOSFET. Okay. So because the safe operating area is more in MOSFET, requirement of snubber circuit is reduced. So statement D is also right statement. Statement D is also perfect. So what are the answers? A, B and D. So answer is A, B and D. So you have three statements are correct here. Dear students, three statements are correct. Okay, A, B and D. So these are multiple select questions, dear students, multiple select questions. So I hope it is very clear to you. A, B and D is the right answer. So I hope everything is clear to you. Yeah, D is also true, Chandan. D is also true. Okay, is it fine? Yeah, okay. So I hope everything is clear to you. The next question. Yeah, go through this question. Dear students, please go through this question. Can you identify what is this DC to DC converter? Dear students, first of all, if you go through the question, this question belongs to what? So DC to DC converter, is it buck or is it boost converter or is it buck boost converter? Dear student, just look at the circuit diagram. Look at the circuit diagram and tell me what type of converter it is. Is it buck converter? Is it boost converter or is it buck boost converter? Yeah, what is your answer? Exactly, students. So what is the circuit diagram? So this is a buck boost converter. Okay, this is a buck boost converter. Fine. So in this converter, the duty ratio of the switch is 0.4. In some textbooks, capital D, 0.4. And operating frequency is 20 kilohertz. Operating frequency. Assume all components are ideal. All components are ideal. Find out the peak to peak ripple current in the inductor. So here, so current is passing through the inductor. So let this current is IL. So we have to find out the peak to peak ripple in the inductive current. Yes, dear students, all of you try this one. Yes, very wonderful question. Find out the peak to peak ripple in the inductive current. Yes, make it fast. Find out the peak to peak ripple in the inductive current. Yes, students, make it fast. Find out the peak to peak ripple in the inductive current. Very simple question. Yes. Find out the peak to peak ripple in the inductive current. Yes, Abhishek Sharma, your answer is perfect. Yes, right answer. Kaushik, your answer is also right. Exactly, perfect. Hari Prasad, your answer is right. Exactly, you are fast. Okay. Yes, any other answers from your side? Ankit, yes, you are also right answer. Yes. Very good students. So just look at this converter here. in the first mode when the switch is on, how the inductive current will increase? First of all, how the inductive current will increase? How the inductive current will increase? So it is a buck boost converter. Just listen to me. It is a buck boost converter, no? What is the formula for average voltage? Average voltage is alpha Vs by 1 minus alpha. This is applicable if it is continuous conduction. This is also applicable when it is at the boundary. Okay. So let us calculate this value. Alpha Vs by 1 minus alpha. Alpha is 0.4 into supply voltage is 100 volts by 1 minus 0.4. Dear students, calculate this value. Let us see. Calculate this value. Yes. $66.66 volts. So this is 66.66 volts. But given V0 is 100 volts. So here given V0 is 100. So V0 is greater than alpha Vs by 1 minus alpha. So therefore IL waveform is continuous conduction, not discontinuous. So IL waveform is discontinuous conduction here. Okay. First step is we have to identify whether it is continuous or discontinuous. IL waveform is discontinuous conduction. Okay. IL waveform is discontinuous. See here, when you turn on the switch, in this mode, what is the KVL? Vs is equal to L into di by dt. Okay. L into di by dt. So di by dt is equal to Vs by L, 100 by L. So that means the current is linearly rising at a slope of 100 by L. The current is linearly rising at a slope of 100 by L. So up to here the switch is in the on state. That is called turn on time of the switch. How do you find turn on time of the switch here? In the first mode, turn on time of the switch is alpha into time period. Alpha is 40%. Duty ratios, that means the switch is in the on state for 40% of the cycle. And what happens when you disconnect the switch here? When you disconnect the switch here, in the second mode, inductive current freewheels through the diode. So this is the second mode. So in the second mode, when you disconnect the switch, VL will become negative. So L is discharging energy, VL is minus 100 volts. So that means the current is linearly discharging. So current is linearly discharging at a slope of minus 100 by L. This is the extinction time, beta into T. After that it will be discontinuous. So what we have to find out here? We have to calculate the ripple in the inductive current. See here, we have to calculate the ripple in the inductive current. Yes. How do you find out the peak to peak ripple, students? How do you find out the peak to peak ripple in the inductive current? Yes. This is a buck boost converter. Buck boost converter. What is the ripple in the inductive current? The ripple in the inductive current is alpha into Vs by F into L. In the case of buck boost, alpha is 0.4 into DC supply is 100 volts by what is the value of frequency? Frequency is how much? 20 kilohertz. Frequency is 20 kilohertz. So 20 into 10 power 3 and 20 milli, 20 into 10 power minus 3. So let us calculate this value. Yes students, calculate the value. So what is the answer? Yes, answer is 0.1 amperes. Okay, 0.1 ampere. So here the first point is you have to check whether it is continuous or discontinuous. Okay students, right students? Yes, try to find the next question. Go through the next one. Yeah, next question. Yes students, all of you try to solve the next question. A sinusoidal voltage source is given. It is applied to a non-linear load resulting in non-sinusoidal supply. So okay, fine. So look here. This is a non-linear load. Non-linear load, okay. So supply voltage is 100 cos. See, this is the supply voltage. This is 100 cos 377 into T, and they are given the supply current. They are given the supply current. Okay, this is AC side. So we have to find out the distortion factor of supply current. Yes, all of you find out the distortion factor for the supply current. Yes students, make it fast. Find the distortion factor for the supply current. Okay, find the distortion factor for the supply current. Yes, make it fast. Find the distortion factor for the supply current. Okay students, yes, Abhishek, your answer is right. Hari Prasad, your answer is right. What about remaining guys? So load is a non-linear load. Supply current is distorted with AC components at different frequencies. See here. Here fundamental frequency is, what is fundamental frequency? Fundamental frequency is 377. Okay, that is fundamental frequency. So this is the fundamental component of source current. See students, harmonics are there here. This is the DC quantity. This is the fundamental source current. And what is this frequency here? 3 omega. What is 3 omega? So 3 into 377. So what is this value? Double 131, right? Yes. So this is the third harmonic source current. Dear students, this is the third harmonic source current. What is this frequency? Calculate 5 into omega. This is 1131. What is 5 omega? 5 into 377. Okay. So 5 into 377 1885. Yes, this is also 1885. Yes, this is the fifth harmonic component. This is the fifth harmonic component. So we are having DC component, fundamental component, third harmonic component and fifth harmonic component. I want to find out the distortion factor for the supply current. So look here. So what is the distortion factor? Distortion factor for supply current, that is equal to fundamental source current RMS divided by RMS value of all the components. So this is the formula to calculate distortion factor. What is fundamental RMS current? Fundamental amplitude is 15 amperes. So fundamental RMS is 15 by square root of 2. 15 by square root of 2, fundamental RMS. What is supply RMS current? Dear students, how do you find supply RMS current? We are having harmonics at different frequencies. Now I want to find out the RMS value due to all the components. See, how do you find RMS value due to all the components? See here, supply RMS current is square root of DC 8 square, fundamental RMS is 15 by root 2 whole square. Then next 6 by root 2 whole square, 6 is amplitude now, 6 by root 2 whole square plus fifth harmonic RMS 2 by root 2 whole square. Okay, so calculate this value and substitute there. Okay, fine. What is the answer? Substitute here, square root of 8 square plus 15 by root 2, 6 by root 2, 15 by root 2 whole square plus 6 by root 2 whole square plus 2 by root 2 whole square. Just simplify this. So that is 0.6, right? 0.76 amperes. 0.76. Okay. So distortion factor is very low. So that will increase the harmonic content in this case. Okay, fine. Yeah. So go to the next question now. Okay, students. Yes, all of you try this question. Tell me what type of DC to DC converter it is. Is it buck converter or boost converter or buck boost? Just convey the message to me what type of converter it is. Yes, make it fast. What type of converter it is? Yes, buck converter. Try to solve this question. Hello students, all of you try to solve this question. Just try to solve this question. I will give 2 minutes to you. I will be back after 2 minutes. Just 2 minutes I will give time. Yes, make it fast. So we have to find out the peak current passing through the switch. The filter inductance is 25% larger than the minimum value of inductor to ensure current is continuous. Okay, so the filter inductance is 25% larger than the minimum value of ensure inductance. Minimum value to ensure, this is a small printing mistake here, see, 2, yeah, small printing mistake. The filter inductance is 25% larger than the minimum value to ensure inductor current is continuous. Assume all components are ideal. Let us assume all components are ideal. Let us assume all components are ideal. Let us assume all components are ideal. Okay. Yes, make it fast. Very wonderful question, student. Yes, Abhishek, did you get the answer? Yes, students. Yeah. What is the answer? See, the filter inductance is 25% more than the minimum value to ensure that inductor current is continuous. So what is the value of L here? Just look here. The value of L is 25% larger than minimum inductance required for getting continuous conduction. 25% larger than minimum inductance required for continuous conduction. So what is the minimum inductance required to ensure continuous induction? See, this is nothing but critical value, no? This is nothing but critical value of inductance. Critical value of inductance. Critical value of inductance, that is nothing but LC. So therefore L is equal to 1. See, L is equal to 25% more, no? So 1.25 times LC. So find LC here, dear students. Find LC. I gave you the hint. Find LC. First of all, we have to find LC. What is critical inductance? Critical inductance means it is a minimum value of inductance that is required to make the inductive current at the boundary, continuous conduction. So how do you find critical value? At critical inductance, IL waveform is at the boundary. See, at critical inductance, IL waveform is at the boundary. IL waveform is at the boundary. I hope you understood. At critical inductance, the value of IL waveform is at the boundary. Let me show you the IL waveform here. When it is at the boundary, IL waveform is like this. This is the time period. Okay. This is maximum value, I maxima, and that is the ripple, delta IL. Okay. Now, how do you find IL average at the boundary? IL average at the boundary is delta IL by 2. It passes through the midpoint of the ripple. This is IL average at the boundary. IL average at the boundary is delta IL by 2. Dear student, this formula is applicable only at the boundary. Okay. So how do you find ripple for buck converter? For buck converter, ripple in the inductive current is alpha into 1 minus alpha into Vs by F into L. Okay. Now one more point. In the case of buck converter, IL average at the boundary is same as output current at the boundary. So delta IL is alpha into 1 minus alpha into Vs by Fl. So 2 into F into Lc. I naught can be written as V naught by R. R is the load resistance. Okay. So right hand side, alpha into 1 minus alpha into Vs by 2 into F into Lc. So both the sides Lc gets cancelled. Wait. So here what is V naught here? V naught is equal to alpha Vs. So V naught is equal to alpha Vs. Alpha Vs by R is equal to alpha into 1 minus alpha into Vs by 2 into F into Lc. Okay, fine. So both the sides alpha and Vs will cancel, and from this we can write Lc is equal to 1 minus alpha into R divided by 2 into F. Okay, fine. No need to memorize this formula. Just understand the boundary conditions, you will get it. Just understand the boundary condition. So calculate the critical value of L, 1 minus alpha into R by 2F. So how do you find alpha here? See here, how do you find alpha? V naught is equal to alpha Vs. This formula is also valid at the boundary. Of course, even for continuous conduction it is valid. So alpha is equal to V naught by Vs. Okay. So calculate the value of alpha. 18 by 48, 0.375. 18 by 48. So that is the value of alpha. So find out the critical value, 1 minus 0.375 into, what is the load resistance here? Load resistance 10 ohms. Okay. So load resistance is 10 ohms. Load resistance is 10 ohms by 2 into the frequency is 40 kilohertz. Okay. Frequency is 40 kilohertz. So 40 into 10 power 3. Yes, calculate the value of critical inductance. How much you are getting? Yes, students, how much you are getting? Yes, make it fast. So critical value is 78.12 microhenry. Yes, 78.12, calculation mistake, Joy. 78.12 microhenry. 78.12 microhenry. Okay. Now given L is equal to 25% of LC. That means 1.25 times greater than LC. What is LC value here? Already we calculated critical value. It is 78.12. Okay, 78.12. So let us calculate this value. How much you will get? Yes. So 97.65 microhenry. So that is the L value. It's not LC, L value. Yes. So next what we have to calculate? Find the peak current that is passing through the switch. So just look here. See, up to T on, switch will conduct. Second mode, diode will conduct. So here, the peak value of current passing through the switch is same as I maxima. That is same as I maxima. Okay. And what is I maxima? Delta L. Yes. Try to find out this. So first of all, we have to calculate. Wait, students. Yes, see here, L is greater than critical value means it will be continuous conduction, no? See here, small correction, my dear students. Here, this is at the boundary, for boundary value, right? Now, peak current in the switch is, I maxima plus delta L by 2. This formula is valid for continuous conduction. Okay, see, L is greater than critical value, no? So that is why it is continuous conduction. L is 25% greater than critical value. That is why it is continuous conduction. Yeah, that is true. So what is I maxima? IL average plus delta L by 2. IL average is I naught plus delta L by 2. Yes, calculate this value. What is delta L here? Calculate the value of delta L. Yeah, calculate this value, students. What is the value of delta L? 0.375 into 1 minus 0.375 into 48 volts is the supply by frequency. Frequency is how much? 40 kilohertz. Okay, 40 into 10 power 3. And the value of inductance is how much it is? (97.65 microhenry). 97.65 microhenry. So calculate this value, students. What is the value of ripple? 2.88. Yes, 2.88 amperes. So that is the formula for ripple when it is continuous. Okay. Yeah. Now peak current passing through the switch is, what is I naught? V naught by R. For resistive load, V naught by R plus ripple current is 2.88. See, plus 2.88 by 2. 2.88 by 2. V naught is 18 by 10. 18 by 10 plus 1.44 plus 1.44. 1.8 plus 1.44. 1.8 plus 1.44, 3.24 amperes. So you will get 3.24 amperes. So that is the peak current passing through the switch. Very good question. Okay, that is the peak current that is passing through the switch. Peak current passing through the switch. Okay, students, the peak value of current passing through the switch. So once again go through this question, all of you. Dear students, just go through the solution for this. Okay, fine. Once again verify the calculations. I hope you are getting 3 point, how much? 3.24 amperes is the right answer. Okay, students. So go through the next question. Dear students, this is also very simple question. All of you try this question. Make it fast. TUF means transformer utilization factor. See here, TUF means it is transformer utilization factor. For half wave rectifier shown in the figure, it is 0.2865. Okay, so we have to find out the volt ampere rating of transformer. Yes, make it fast. We have to find out the volt ampere rating of transformer. Yes, students, make it fast. also find PIV rating of diode, students. Same question, one more question I will add you here. Find out the PIV rating of diode. Find out the PIV rating of diode. Dear students, one more question I am adding here. Okay, find out the PIV rating of diode. Okay, find out the PIV rating of diode. Find out the PIV rating of diode. Okay, so try to answer these two questions. So I have added one more question here. Find out the PIV rating of diode. Yes, I will explain what do you understand by PIV rating. Yes, try to answer these two questions. Yes, make it fast. See, in gate examination, the weightage for power electronics varies in between 8 marks to 12 marks. Okay, minimum 8 marks, maximum it will go even up to 12 marks. So mostly 5 to 6 questions they will be giving. Okay, around 5 to 6 questions they will be giving in power electronics. Weightage will be 8 marks to 12 marks. Okay, yes, make it fast. Abhishek Verma, PIV is wrong. Yes. So what is the meaning of PIV rating? It is the maximum negative voltage that appears across the diode. Okay. Okay, shall we start? Yes, now look here. How to find transformer utilization factor? All of you write down the formula for transformer utilization factor is power due to the DC components divided by volt ampere rating of transformer. Okay, see here, TUF is equal to power due to the DC component divided by volt ampere rating of transformer. I have given you the hint, so I hope now you can answer this question. Abhishek Sharma, please verify once again. You done some mistake. See, what is the power due to the DC component? This is output voltage, this is the voltage across the diode, this is our supply voltage. Okay, fine. What is the waveform for supply voltage, which is sinusoidal here? So what is the peak voltage of AC supply? The peak voltage of AC supply, transformer ratio is 1:2. So secondary voltage is twice the peak voltage now. So this is actually RMS value here. on primary side RMS value 230. So 1:2 no. So this voltage is 230 means this is 230 means this is 2 times 460. Okay, see transformer ratio is 1:2. Primary voltage is 230, secondary voltage is 1:2 ratio. So double, so 460 volts. Of course, AC parameters are normally expressed in RMS. So 460 is RMS value on secondary side. Its peak value is 460 root 2. Its peak value, okay, 460 root 2. Now let us draw the waveform for output voltage here. It is a half wave rectifier with resistive load. So you will get only half cycle here, and remaining half cycle you will get 0. You will get 0. Okay, this is Vm. Okay, so here for this average voltage is Vm by pi, because it is half wave rectifier. Average voltage, average current is average voltage by load resistance, that is Vm by pi into R. So that is the power due to the DC component. So therefore the power due to the DC components is given by V0 into I0. Okay students, the power due to the DC components is V0 by I0. Dear students, it is a resistive load now. Dear students, yes, how much you are getting here? Vm by pi is 460 root 2 by pi. See, what is this value? 460 into root 2 by pi. This is 460 into root 2 by pi. So what is V0 here? 207.047, right? Please verify this value. Dear students, verify this value. Let me calculate this. 460 root 2. Divided by pi. So 207.07, right? 207.07 volts. 207.07 volts. So this is 207.07 volts by load resistance given is 60 ohms is the load resistance. Okay, so calculate this value. So 3.45 amperes. 3.45 amperes. Okay, 3.45 amperes. So what is the power due to the DC components? V0 is 207.07 into 3.45 amperes. So calculate the power due to the DC component into 207.07. So that comes to 714.64. 714.64 watts. Okay, so from this equation I want to find volt ampere rating of transformer. Volt ampere rating of transformer is power due to the DC component divided by transformer utilization factor. So what is the power due to the DC component? It is 714.64. 714.64 divided by 0.2865. Yes, let us calculate this value. Okay, how much you are getting? 2494. 2494. Two four nine four point 3 volt amperes. Okay students, everyone got the same answer? Okay, fine. So also find out the PIV rating of the same diode. Dear students, also find out the PIV rating of the same diode. Yes, make it fast. PIV rating of the same diode. See, in Bimra textbook, they have given a tabular column specifying the transformer utilization factor for different types of rectifiers and loads. You can verify that one. Okay. Abhishek Sharma, I hope you understood. It is given in Bimra textbook, transformer utilization factor for single phase half wave rectifier, resistive load. Okay, single phase full wave rectifier, 3 pulse converter, 6 pulse converter. They have mentioned the transformer utilization factor. You have to remember that even if it is not given. See, transformer utilization factor you have to remember. Sometimes it may not be given. Okay. Yes. Now what is the PIV rating of diode? See, to find out the PIV rating of the diode, find out the voltage across the diode here. See here, in the negative cycle, when diode is in the off state, see here, diode is conducting in the positive cycle. Here diode is in the off state here. Here diode is in the off state here. So let us draw the waveform for voltage across the diode. See, up to pi radians, since diode is in the on state, let us assume ideal diode. See, when diode is in the on state, if I assume that it is ideal diode, its drop is 0 volts. If I assume it is diode, and voltage across the diode same as the supply voltage, no? Same as the supply voltage. So this is the waveform for voltage across the diode. Now what is the PIV of the diode? PIV means what is the maximum negative voltage of diode? It is the peak voltage of AC supply, that is nothing but 460 root 2. Yes, let us calculate this value. So 650.53 volts, 650.53, okay. So 650.53 volts. Okay students, yeah. So peak inverse voltage rating means it is the maximum negative voltage that appears across the diode when it is in the off state. Okay, so concept is clear students. Okay, fine. Yeah, try to find the next question. Yes, answer the next question. Go through the next question, all of you. Dear students, try to answer this question. This is also very wonderful question. They are asking to calculate the peak instantaneous output voltage. So first draw the waveform for output voltage. In that waveform they are asking the peak value. Okay? Yes, make it fast. See, students should understand how to draw the waveform at different values of alpha, without which you cannot answer such type of questions. Yes, try this. Hello? Yes. So now I am audible, right? Yes, all of you try this question. You just solve this question. This is really a wonderful question. Yes, make it fast. Draw the waveform, dear students. When the firing angle is 60 degrees, draw the waveform for output voltage. You will get the answer. When the firing angle alpha is equal to 60 degrees, draw the waveform for output voltage so that you will get the answer here. Okay? Yes, make it fast. Yes, students. Yes, make it fast. Yes, Kaushik, your answer is right. Yes, make it fast. Many students repeat the same mistake, I know. Unfortunately, same mistake is repeated by many students. Be careful with such type of questions, my dear students. Very simple, but many students doing the same mistake again and again. Be careful. Try to understand the question clearly. First you draw the waveform for output voltage and you will get the peak value, okay? Yes, Jitendra, your answer is also right. Mr. Jitendra, your answer is also right. Yes. Abhishek, please check once again. Yes, make it fast. Yes, all of you draw the waveform for output voltage, you will get the answer. Yes, all of you look here. So let me draw the waveform for output voltage. See here. Waveform for output voltage, okay? This is the freewheeling diode, okay? This is R phase, Y phase, B phase. So power supply is 220 volts. That is the RMS value of line value. See, AC quantity, whenever there is a supply voltage and it is mentioned 3 phase, by default it is line RMS value. By default it is line RMS value. So understand the question. Whenever 3 phase supply is specified, if they do not mention anything, by default take it granted that it is a line voltage RMS value. Now firing angle alpha is equal to 60 degrees. See here. First of all, lower limit is 30 plus alpha and upper limit is 150 plus alpha. These limits are valid for reference pulse. Our reference pulse is VR phase. Now alpha is equal to 60 degrees. So at alpha is equal to 60 degrees, lower limit is 30 plus 60, lower limit is 90 degrees and upper limit is 150 plus 60, upper limit is, how much it is? 210 degree. Okay, so waveform is like this. Waveform starts at 90 degrees. See here, lower limit is 90 degrees, sine 90, and somewhere here 180 degrees. So this is Vm. This is the R phase voltage. Okay, this is the R phase voltage. This is the R phase voltage after 180 freewheeling period up to upper limit. Here freewheeling diode is conducting, 0 voltage you will get. This is the waveform. Okay, at 90 degrees we get peak phase voltage. Okay, so therefore the instantaneous output voltage is, the peak value of instantaneous output voltage is the peak phase voltage. How do you find out the phase voltage? Given line voltage RMS, no? So here, what is the peak line voltage? It is 220 into square root of 2. That is the peak line voltage. So what is the peak phase voltage? Phase voltage is the peak line voltage divided by root 3. Divided by root 3. So this is 220 into root 2 divided by root 3. So answer is 220 into square root of 2 by 3. Okay, so answer is option B. Okay, fine. So normally people will say answer is 220 root 2. Many students are mistaken here. Most of the students are generally mistaken here. Okay, so be careful, my dear students. So I hope answer is clear. Yes. Okay, students. See here, to answer such type of questions, you must understand the shortcut method. I have explained in the regular course. Just by understanding the limits, you can imagine the waveform and write down the answer. If you don't understand this shortcut method, then it will consume your valuable time. For gate examination, try to remember the shortcut methods also. Okay, right. Then next, go through the next question, student. Dear students, see the next question. The output voltage of a three-phase VSI contains fifth and seventh harmonic components. The output voltage of three-phase VSI contains fifth and seventh harmonic components. See here. This is the waveform for output voltage. Okay, so here fundamental component. So this is the fundamental, fifth harmonic frequency, seventh harmonic frequency. So this is actually the output voltage, right? No, VA. This is phase A, dear students. This is nothing but phase A. It is given, you see. This is the voltage of phase A. Now, what we have to find out? VB can be expressed as. So how to express VB here? How to express this VB here? How do you express VB? See, VA you know, VB we have to find out, and VC we have to find out. So just look here. For a three-phase balanced system, okay, so suppose this is VA taken as reference vector, with reference to phase A, phase B lagging by 2 pi by 3, okay, phase B is lagging by an angle 2 pi by 3 radians, okay, and then phase C if you see, this is lagging by an angle 4 pi by 3. It is lagging by 4 pi by 3 means it is leading by 2 pi by 3, meaning is same. Okay, see, phase C is lagging by 4 pi by 3, that means it is leading by 2 pi by 3. So now let us find phase B. How do you find phase B here? So just look here, phase B voltage is lagging phase A by 2 pi by 3. See here, with reference to phase A, phase B is lagging by 2 pi by 3. So B phase is phase A. This is the equation for phase A. First fundamental component, fundamental magnitude, sine of omega t, sine of omega t minus lagging by 2 pi by 3. Lagging by 2 pi by 3. That is the fundamental. Then how do you find fifth harmonic amplitude? Fifth harmonic amplitude, sine of 5 times omega t. Okay. 5 is taken common now. Dear students, 5 is taken common here. See here, sine of 5 is taken common. This angle is omega t minus 2 pi by 3. Okay? See, 5 times off. Then seventh harmonic angle is 7 times off. See here, what is seventh harmonic angle? V7m sine of 7 into omega t minus 7 into omega t minus 2 pi by 3. Okay, let us simplify this value. I can rewrite this value as sine of 5 into omega t minus 10 pi by 3. Okay, I can rewrite this value as sine of 7 into omega t minus 7 into 2, 14 pi by 3. 14 pi by 3. 7 into omega t minus 14 pi by 3. Okay. Now how can you write 10 pi by 3? See here. You can write 10 pi by 3 like this. Just look here. See the phasor diagram. Just look here. This is 0. This is lagging by 2 pi by 3. This is lagging by 4 pi by 3. Lagging by 6 pi by 3. Okay. Lagging by 8 pi by 3. 8 pi by 3. Lagging by 10 pi by 3. So minus 10 pi by 3 means that is equivalent to 2 pi by 3. So dear students, see here, 0, minus 2 pi by 3, minus 4 pi by 3, minus 6 pi by 3, minus 8 pi by 3, minus 10 pi by 3. Minus 10 pi by 3 means that is same as plus 2 pi by 3. So I can rewrite this expression like this. This can be written as sine of 5 into omega t plus 2 pi by 3. This is also right. You can use this one or this one or this one. Similarly, this one is written as sine of 7 omega t. What is minus 14 pi by 3? See here. Minus 10 pi by 3. Minus 12 pi by 3. Minus 12 pi by 3. And minus 14 pi by 3. That is lagging by 2 pi by 3. So minus 2 pi by 3 I will write. So sine of sin from minus 2 pi by 3. Okay. So what is this one? So I hope you understood. So what is the answer here? Yes, now verify students. plus 2 pi by 3. See, this is plus 2 pi by 3, this is minus 2 pi by 3. Yes, yes. First one is plus B phase plus 2 pi by 3, no? Yes. See, minus 10 pi by 3 is plus 2 pi by 3. You are given minus 2 pi by 3, wrong. This is also, okay. So this is wrong. A is wrong. B plus 2 pi by 3 minus 2 pi by 3. Yes, B is right. Dear students, option B is right. Okay, fine. Go through the question number. Go through the next one. Phase C. I want to find phase C. See, how do you find phase C? Phase C, you just see here. How do you find phase C? Lagging by 4 pi by 3, no? So look here. Phase C lagging phase A by 4 pi by 3. So Vm1 sine of omega t minus 4 pi by 3 radians. Minus 4 pi by 3 radians plus fifth harmonic component V5m sine 7 is common omega t minus 4 pi by 3 radians plus seventh harmonic component V7m sine 7 times of omega t minus 4 pi by 3 radians. So okay, I can write this one as sine of 7 omega t minus 7 into 4, 28, right? Sine of 28 into pi by 3 plus this one. How to write this 28 into pi by 3? Yes, so look here. So minus 14 pi by 3, again minus 16, 18, 20, 22, 24. How much it is there? Up to 28, no? See, 24, 26, 26, 28. So 28 pi by 3 is here. So just look here. Here minus 6, 12, 18, 24, no? 24 pi by 3, then minus 26 pi by 3 and minus 28 pi by 3. Minus 28 pi by 3 is 2 pi by 3. See here, minus 28 pi by 3 is 28 pi by 3 is 2 pi by 3, right? So I think this is right, this is wrong, okay, that is wrong, okay. And similarly, what about seventh harmonic frequency? Seventh harmonic you see here, seventh harmonic you see here. Small correction, my dear students, this is 5 times, this is 5 times, 5 times, 7 times means this one. Here sine of 7 omega t minus 28 pi by 3, this is sine of 7 omega t plus 2 pi by 3. Okay, this is wrong, okay, this is for this one. Yeah, now what about this one? Sine of 5 omega t minus 20 pi by 3. What is 20 pi by 3 here? Just look here, 20, where is 20? This is 18, 18, 20. See here, 6, 12, 18 pi by 3. So here we get 20 pi by 3. That is lagging by 2 pi by 3. Okay, that is lagging by 2 pi by 3. So sine of 5 omega t minus 2 pi by 3. Yes, now verify this one, which is right answer. First minus 2 pi by 3, minus 2 pi by 3 plus 2 pi by 3. Yes, small correction here, this is wrong here. Okay students, so this is right, this is right. So B and D is the right answer. Okay students, so I hope everything is clear. Are you having any doubts? Yes. That's all. Yes, now go through this. So this is also MSQ questions, okay? Right students? Okay, my dear students, with this we have completed all the questions. So normally the weightage in gate examination for power electronics, minimum 8 marks, maximum it goes up to 12 marks also. So the weightage of power electronics, mainly we have to concentrate rectifiers, choppers and inverters. Okay? So in the first chapter, power semiconductor devices, hardly 1 mark they will ask, or at the most 2 marks, not more than that. Okay? So mainly the problem for power electronics is how to remember the formulas. You go through, in Made Easy I have given this QRC program, right? You can go through the QRC program, quick revision course, okay? Quick revision course for power electronics. Okay, quick revision course for power electronics. In this quick revision course, so for each chapter I have given the summary, what formulas we have to memorize, how to memorize the formula, where the formula is applicable, how to solve the questions. Okay, just it is only 5 hours. Regular course I have taken up to 80 hours, but quick revision course only 5 hours topic. If you go through the quick revision course for power electronics, you can write down the short notes so that it will be very much helpful before examination. Okay students, so be confident, don't read any new textbooks at the end. You are at the end now, so already whatever you have studied in the past, revise it once again. So try to memorize the things and try to remember the formulas in a convenient order as I have given in the QRC program, so that it will be easy for you. Okay students, all the best my dear students. Okay, thank you. If you have any doubts you can ask. All the best. Okay students, are you having any doubts? All the best. Yeah, I already said to you, rectifiers, inverters and choppers, very important topics. Okay. Hello.